He is a professor, associate professor in mechanical engineering, and we are very happy to have him today. And I call upon Dr. Chetan, who is our Honorable Secretary, to call the guest on the dais. Now I call Dr. Chetan to introduce the speaker and we will start the session.
Very good evening, all of you, to IEI Institute of Engineers Kgp Local Chapter. Today we have with us Dr. Mahendra Reddy. So, as a part of a session, every month we will be having invited and special talk by the experts from different domains. Today we have with us Dr. Mahendra Reddy. He is an associate professor in Department of Mechanical Engineering, IIT Kharagpur, where he has been faculty member since 2017. He obtained his PhD in Aerospace Engineering from IIT Bombay, specialization in new combustion technologies such as flameless combustion with liquid fuels. After his PhD, he worked for 3 years as postdoctoral fellow at the Clean Combustion Research Center at Coast, Saudi Arabia. Dr. Reddy's research interests are diverse and it includes droplet and splay combustion, flameless combustion, high pressure combustion, swirl combustion, ammonia combustion, hydrogen combustion, and porous media combustion for cooking and gas turbine applications. He has authored over 60 publications in reputed journals and 50 in conference proceedings. Dr. Reddy has graduated 8 PhD scholars. His contributions have been recognized with the numerous awards, which includes Excellence in PhD Thesis Award from IIT Bombay in 2014, MI TR35 India Young Innovator Award in 2012, 6th ITERIA Award for Sustainable Energy and Power in 2012, and twice selected for the Seoul National University BK21 for project in 2023 and 24. Dr. Reddy has been invited as visiting research professor in University of Louisiana, USA. With this short introduction, let me call combustion man of IIT Kharagpur, Dr. Mahendra Reddy.
Good evening, everyone. So first of all, I am very thankful to Engineers India Local Chapter of IIT Kharagpur. So today, let us discuss about challenges in non-carbon fuels like hydrogen and ammonia in industries as well as gas turbine engines. Let us see over here. So combustion is the first research of humankind. As you know, the flame has been identified, or combustion or fire has been identified. Then our civilization has been started. Then from this particular location to this location, this particular duration was thousands of years. So we were not worrying about very much. Then after, the energy efficiency to be increased and at the same time polluted emissions to be decreased. That was our primary goal. So then finally we have moved towards a clean combustion, right? Then after sophisticated combustion technologies we have moved. But still, the burning the fuel of hydrocarbon fuel is still the problem, right? So suppose now why we need to focus upon the particular sectors like industries and automobile and transportation means this is the scenario. Out of that, the total amount of sharing of this particular sector. So now what we are doing to regulate these particular emissions, so we have been formed certain emission indices. Earlier we used to follow BS stage, means Euro stage. So now we have moved to the Bharat stage, our own, right? So now this is the difference between the 4 and present is going on 6. 6 even not completely implemented upon all the combustion systems. However, if you see over here, achieving this particular 4 means BS4 norms itself was very difficult. If you see over here, this is the 0.63 gram per kilometer for case of CO. In case of 6, the same standard has been maintained. That means even though this stage has been changed, the reduction of CO furthermore is very challenging. But however, NOx emissions to be decreased. Okay. So in case of 4 and 6, this is the changes in the NOx emissions. Now what to do next? What is happening now? The population is increasing. Okay. Even our comfort zone is also increasing. Comfort zone means number of AC applications as well as your vehicles, right? And all other things are increasing continuously. Then, however, we are in the stage 6, our net emissions are keep on increasing. Means it is cumulative. Okay. So now what to do? We have to find out certain thing like non-carbon phenomena. Or now before going to that, let us see what are the problems with this CO and NOx. Suppose this is the CO and it is exposing hours, then this much of particular CO and exposure time, how much amount of carboxyhemoglobin is forming in our blood, right? If you see over here, for case of 100 ppm, if we are exposing around 2 hours, 3 hours, then we will be feeling headache. This is condition of what? So you are stuck in the traffic and the traffic is very slowly moving, okay? So and then this is the condition. So you will be getting headache, okay? So then if this is the situation like you are working in the plant, all of a sudden certain combustion systems have been gone off, okay? So now you will be fighting over there, what is the happen, means what is the situation over there. Meanwhile, this much of even 1 hour of exposure is sufficient for probing headache, right? And then if it is around 600 ppm, this is the much dangerous condition, even less than 1 hour. So this is like a coma, okay? So now, okay, these are not the severe cases, even can be identified, but these cases are like even number of vehicles are increasing continuously, the net amount is increasing from this to this in the atmosphere, right? So that is one. In case of NOx, what is happening? Even this NOx footprint is dangerous than your CO footprint. Okay. So because of the NOx, your inhaling system. So what is these particular tubes are cladding with mucus. Then when you are inhaling and exhaling, you are feeling certain situation like irritation. That irritation is giving you cough. Okay. So this is one particular phenomena. Now to what to do this particular phenomena? So then many researchers have been started working upon this particular like IEI combustion. Okay, IEI means high temperature combustion. Okay. If you see over here, this is the temperature of the furnace, right? And even this case suppose temperature of the furnace, same time emissions also high. But however, this particular case, efficiency was very high, right? Then, but still, emissions are certainly high, efficiency is increasing, but how to reach this particular? We are not much worried about this. The combustion should be stabilized very well, and the emission should be low enough. Okay, then how to achieve this? This is one novel technique of hydrocarbon fuels, that is called the flameless or mild combustion or colorless distributive combustion. People can call different nations like that. So now, how the NOx formation is taking place? If you see over here, the NOx basically categorized it into 3 phenomena. The first thing is the fuel NOx, thermal NOx, and prompt NOx. The name itself is telling thermal NOx, means this NOx is very well related with temperature. If temperature is increasing, the NOx concentration also keep on increasing. Okay. Another one is fuel NOx, that you know, if nitrogen is there in the fuel, okay, when that is cracking phenomena is happening inside, that is forming the NOx. Okay. The next one is prompt NOx. This is not very much dangerous because at the beginning of the reaction it is happening, then it will be controlling itself as like other NOxes. Okay. Now this particular thermal NOx, what is happening here? Whenever temperature is above 1800 Kelvin, right? Then your nitrogen means N2 is splitting into N and N, and oxygen is splitting into O and O. Then these kind of reactions are severe over there, like N2 plus O forming NO, plus N plus O2 forming again NO. Okay, this particular NO is called NOx, as you know very well, right? So this particular reaction can be called as Zeldovich mechanism because whoever the scientist has been identified long back. If you want to suppress this thermal NOx, you have to maintain your temperature below 1800 Kelvin, right? So now, in case of our combustion system, when you are running your combustion in the low temperature, like we can call it as a lean combustion, right? So obviously, your NOx is very low because the furnace temperature is less, or otherwise the combustor temperature is less. That's what NOx emissions are less. But what is happening? Unburned fuel means, or otherwise unburned CO is dominating over here. Means CO, whatever is formed from the fuel, is not consuming completely, right? On other side, if you go over here for a higher temperature side, what is happening here? The CO is completely consuming, but still NOx emissions are high over here because the NOx is directly related with temperature, right? Then what to do? Obviously, there is solution. If you run this combustion somewhere over here, then your CO as well as your NOx emissions are low. Okay. So you can say this is the lean combustion. You can say this is around stoichiometric combustion. So in between, that may not be possible very well. Means stabilizing the flame in the conventional flame is difficult over there. So to attain the combustion in this particular zone, the concept of flameless or mild combustion or colorless distributive combustion has been identified. Okay. If you see here, in case of conventional combustion, what is happening? The total energy is releasing in the small volume, right? When total energy is releasing in small volume, obviously flame temperature is very high. So that is this particular high temperature, even more than 1800 Kelvin. Now this is our new technique, flameless combustion. What we are doing over here, we are recirculating combustion products inside the combustor, right? So because of that, what is happening? Inert gases are recirculating as well as certain amount of heat also recirculating, means enthalpy recirculation we can call it as. This enthalpy recirculation is helping you in stabilizing the flame, and these diluvents are helping in distributing the flame, right? Because like here, the oxygen is not directly available. This is distributing over here. That's what your peak temperature is reduced. So whatever so-called NOx formation we can call, the NOx formation is reduced over here, right? This particular phenomena of flameless combustion identified by initially the Wunning et al. So he was actually scientist in particular glass company. So glass company needs the quality or otherwise complete combustion with reduced emissions and all. The clean combustion is required, moreover, if you want to say. When they were experimenting, all of a sudden they have identified this particular phenomenon. Then they have applied certain concepts and they have measured this particular phenomena, how much amount of heat is to be recirculated, how much amount of exhaust gases to be recirculated. If you see over here, this is the conventional combustion and this particular zone is called no reaction. Why it is no reaction? Combustion products are excessively recirculated here, right? So that means over dilution has been done. To stabilize the flame in such worst conditions, the temperature is not sufficient. So reaction was not happening here, right? And this dot zones, like in this zone, the temperature is high enough, but reaction is low enough, means like reactants recirculation is low enough over here. That is the reason flame was not stable. Over here, if you see over here, again the similar condition like no reaction, but temperature is increased, so this particular zone called as unstable flameless combustion or conventional combustion in between. This zone is complete flameless combustion. However, once this particular topic has been identified by Muni, then some prominent researchers have started in this particular direction. So initially, three prominent people like Kasimbi Dari and Professor Sudarshan Kumar from IIT Bombay and even Maradi Jonan from Italy, they have significantly worked upon this particular concept. What the reason behind achieving the flameless combustion? What are the conditions are required to stabilize the flame? These are. So these are the few results of Professor Sudarshan Kumar when he was in PhD for, at IIT Bangalore. So this is my study when I was studying my PhD under the guidance of Professor Sudarshan Kumar again. So far whatever happened here, that is with flameless combustion with gaseous fuels. So in this particular case, achieving flameless combustion is difficult. However, when you compare to the liquid fuel, it is easy, we can call. In case of the liquid fuel, what you need to do, initially the fuel need to be injected as the small droplets. Each droplet need to be evaporated. This evaporated species to be distributed inside the combustor. If the mixer is within the range of flammability, then only flame is stabilizing. Okay. So in case of gaseous fuel, the gas and fuel means gaseous fuel and oxidizer, if mixing very well, then combustion is stabilized. Right? Over here, before that reaction, many sequence of operations are there. These are to be completed. So till those conditions will be satisfying, we have to recirculate the fuel and oxidizer very well inside the combustor. That means, compared to the gaseous fuel recirculation based flameless combustor, in this particular case, the well-stirred reactance is required over here. So why are we explaining this particular flameless combustion concept, which is called well-stirred reactor or perfectly stirred reactor? Means these particular concepts we are going to utilize in ammonia combustion as well as hydrogen combustion in further slides. So this is our flameless combustion with liquid fuel. This is the conventional. So as like other flames you can see over here, this is the flameless combustion. As the name is suggesting, there is no flame over here, means visible flame, right? However, very small flame is visible over here. Otherwise, this is like transparent orange kind of environment was there, right? The flame was stabilizing. Even though this particular combustor was this much big enough, from the top of the combustor, the total combustor can be seen very well, right? So now, this is the recent technique of conventional fuels. Now challenges are like, if you are using the conventional fuels by adopting this technique of flameless combustion or mild combustion or colorless distributed combustion, but still the CO2 is coming, right? When you are running the carbon fuels, the CO2 will be coming out. However, you are minimizing your CO and the NOx, you cannot avoid this CO2, right? That CO2 is causing for the global warming, some other certain causes. Okay. Now what to do? We have to go towards non-carbon fuel. Then what is the strong non-carbon fuel? Hydrogen, right? We have identified hydrogen as the potential fuel for that. Now let us discuss what are the challenges involved with the hydrogen, right? Then let us come back to the ammonia over here. So the first thing is, so this is a very introductory talk. Many students are involved over here. Okay, let us see step by step. So what is called green hydrogen? The green hydrogen means, first thing is electrolysis process we are doing over here. Water electrolysis process means we are taking one anode and one cathode. The water is continuously supplied. Then water is splitting. From that splitting of the water or cracking of the water, the hydrogen and oxygen, okay, rest of the water again coming out, right? To complete this particular process, certain energy is required. Then how to take energy, where to take energy? If we are using that energy from the green resources, like the photovoltaic cells, like solar energy, wind energy, okay, or otherwise hydro energy, okay, non-carbon source of energy. That through that, if you are doing electrolysis process, whatever hydrogen is produced, that hydrogen can be called as the green hydrogen. Okay. Next, pink hydrogen. However, here we are not using this renewable energy sources. We are using here the nuclear sources means carbon content is 0 again, this particular thing is called pink hydrogen, right? The rest of things are actually carbon sources over here, if you see, right? So we are taking natural gas over here, and then we are passing it to a reformer. That reformer we can call it as zone methane steam reactor, okay? So when we are passing to this, then that is cracking again, and hydrogen is coming up, hydrogen you are storing. Now question is like, the hydrogen you are storing, okay, then what to do about the CO2? Otherwise this is a similar phenomena like you are burning the fuel in everything, right? Then why should this much of big electrolysis process or something or otherwise reformer is required over here, right? So whatever CO2 is coming, if you are capturing the CO2, right, carbon capture and storage, right? This is the carbon capture and storage. You are capturing that. Okay, and there is another technique. This is the blue hydrogen can be called. This is a tranquilized hydrogen we call it as. Whenever the captured carbon dioxide or carbon, right? Now you have captured and stored, and again there is a question of what to do that, where to store it. Cylinders of cylinders, the CO2 is coming. Where would you save it? Okay, and again question like, because that is high pressure cylinder, at any time it can last, right? So certain suggestions are like, dump them in the ocean bed, because there the pressure is very high. The cylinder pressure, that pressure both are compensating. Okay, so it is just a normalized tank over there. Then question is, how many will you be dumping over there, right? So in that case, let us convert into carbon block, the solid block. That is the safe solution than this particular, right? So that is your tranquilized hydrogen. The grey hydrogen is obviously storing, and rest of the CO2 is leaving to the environment. Okay, these are different sources of hydrogen. How are you getting? And based upon the source of energy and carbon capture, we have classified them, right? Then, before going to the challenges, let us compare certain factors. I believe that all of the students are somehow related with the combustion and the energy sector, right? So let us see over here. And mechanical engineers at least, or aerospace engineers, right? So over here, if you see over here, the hydrogen has higher calorific value, means compared to other things. Our all fuels calorific value is ranging from 40 to around 45, 30, means 30 to 45 we can call it as, right? Methane has 50, right? So but this hydrogen has almost 120, okay, megajoule per kg. And if you see over here the density is very low, 0.089, right? So I'll give you an example over here. Whatever the cylinder we call in the laboratory, that is the K-type cylinder, around 47 liters you have. That 47 liters, if you are storing at 200 bar pressure, right, then how much gas is there in that particular cylinder can you expect? 800 grams of the hydrogen, just 800 grams. Okay, then what is the cylinder weight? Around 40-50 kgs. When it is 50 kgs of cylinder, that is holding 800 grams, even not more than 1 kg of hydrogen, right? We have started experimenting, right? Then within 30 minutes, the cylinder was over. Then we were surprising that some fault in the connections and all. Then we went and observed over there in the fuel storage side. The cylinder is completed. Then we obviously we know the density and all. Then we calculated only 800 grams of thing is there, 800 grams of hydrogen, and combustor was running at 60 kilowatts. Then we calculated with the time this much of amount of energy it has been already taken. Okay, so that is the problem with that. Okay, so and again certain things like auto ignition temperature. What is auto ignition temperature? You know very well. If fuel and oxidizer is available, okay, and if you don't have any ignition source, only thing is that mixer, if you are keep on heating to certain temperature, wherever that is catching the fire itself, right? That is called auto ignition temperature, right? This auto ignition temperature of this hydrogen is higher than any other fuel over there, right? So far we have higher auto ignition temperature for methane only. Okay, methane or otherwise natural gas. Natural gas content is almost methane, right? So, but this per case of hydrogen, it is higher than that, right? So that is another thing. The quenching distance and all, let us see over here. And one more thing is flammability. The flammability means what? The fuel and oxidizer, you are varying. When fuel is higher, when oxidizer is higher, what you call that as? Equivalence ratio, right? The stoichiometry means what? To run certain amount of the, means to burn the fuel. How much amount of oxidizer is exactly required? In the exhaust gases, the fuel should not be there, right? The fuel will be completely consumed and very minimum amount of CO, whatever according to the combustion norms, should be there, right? So that amount of oxidizer is called stoichiometric here. Whenever you are increasing the oxidizer, that is called lean. Whenever decreasing the oxidizer content, that is called rich. Two limits are there, lean limit and rich limit. For case of conventional fuels, the lean limit is like 0.5 and rich limit is 1.4. Okay, but for case of hydrogen, the lean limit is 0.2, the rich limit is 6.2. Okay, then what is the problem with that? Let it be. That means, in case of our domestic needs, if you have cylinder, the minor leakage is there, even you are smelling, okay, so you will not worry much about. Today or tomorrow you are going to call the mechanic, meanwhile you will be proceeding for the cooking, right? That much, very small quantity won't be damage anything. But in case of this, very small quantity also, if ignition source is there, that will catch the fire. Because it can run even 0.2 equivalence, right? This is the flammability range. And even auto ignition temperature, just now we have discussed. Then what is the problem with auto ignition temperature? In case of, we are talking over here about your internal combustion engines as well as gas turbine engine. Let us take example of internal combustion engines. In case of diesel engine, what is happening? So you are compressing the air, then you are injecting the fuel. You don't have any spark plug over there. Then how it is burning? When you are compressing the air, whatever temperature is there, that temperature is more than auto ignition temperature of your diesel fuel. Okay. Similarly, in case of hydrogen, if you want to bring that situation, right? Even diesel auto ignition temperature is around 280 centigrade. Here it is 500, right? To bring that, in case of diesel already 20 bar pressure we are going. Now you have to go to the 40 bar pressure, right? So then what is the problem in that? Then your system will be bulky, right? These are different challenges are there over there, right? So that is one more thing. And minimum ignition energy. What is the minimum ignition energy? So now my question is like, how are you igniting your gas stove? You have spark, right? So the same whatever lighter, if you install upon your car, would it be working? No. Why it is not working? Obviously the spark may not be sufficient over there, right? Okay, or otherwise it may be over also based upon the condition, right? So like that, based upon this particular condition, particular amount of ignition source is required. Okay. So similarly over here, in case of hydrogen, very small ignition source is enough, right? Suppose in case of domestic needs, when small amount of LPG is leaking, okay, if somebody has not realized that, then after some time somebody is on the plug switch, the spark whatever it is generating, that is creating the problem and fire accidents have been taken place in many cases, right? And here in case of hydrogen if it is, the problems are even fourfolds. Why it is? Even small quantity is sufficient to stabilize the flame. Means lean equivalence ratio is very low, 0.2 for example. And here in case of conventional fuels, the ignition energy is this much, 0.24. But in case of hydrogen, 10 times less than that. Very small source is enough. That means hydrogen is leaking over here, the mixture is even the 0.2. Very small source is available over here, it will start burning. Okay. So another thing is quenching distance. What is the quenching distance? The quenching distance is like in your stove, you might have observed the holes, right? You might have observed the holes. If the hole size is bigger, what will happen? Obviously, flame will go inside, right? The holes have been designed based upon the quenching diameter, quenching distance, we can call it as. Okay. So what is the quenching distance means? If your mixer is pre-mixed, means what is the mixer is pre-mixed? The name itself is telling you don't need to worry much about. The fuel and oxidizer both are mixed very well before the reaction. That is the pre-mixed combustion, right? In case of your gas stove also, that is partially pre-mixed. Okay. When that charge is coming through the holes, the flame is not going inside. The flame is stabilizing above the holes only, right? Such a way it is designed. So what is the quenching diameter means? By mistake, if flame is going inside, okay, if this is the flame volume, if you consider over here, your channel is, it can be cylindrical or otherwise rectangular also, no problem with that. Whatever, this is the flame front or reaction zone. In this reaction zone, whatever amount of energy is releasing, if that amount of energy is completely absorbed by the surrounding material, then flame will be quenched down. Means flame cannot be sustained. That means whatever the energy it is releasing, that has been absorbed. So flame will not stabilize. Otherwise, if energy is more than whatever the losses are there over here, then flame will be happily stabilizing. It has strength, right? That can stabilize here, that can further move inside. Till where it will be moving? Wherever we have fuel source, till there it will move. There, all of a sudden, certain accident will take place, right? So, for every device, if it is operating based upon the pre-mixed nature, then you have to find out for that particular mixer what is the quenching diameter. Now let us see. So this is the quenching diameter scenario over here, right? So for case of these gases, suppose methane, for case of methane, this is at equivalence ratio of 1, that means stoichiometry, your quenching is 1.75 millimeters. Okay? If it is propane, suppose see here, C3H6, propane, this is around 2 millimeters. Your stove, whatever LPG stove, what is the LPG composition? It is a mixture of propane and butane, right? So that's what, upon that, the whole diameter is around 1.75 to 2 millimeters. Okay, so this is. Now, the case of hydrogen, okay, at what pressure your gas stove is operating? Ambient pressure, right? For case of hydrogen, at ambient pressure, right? Where is the ambient pressure over here? So let us take over here these dots. At ambient pressure, the quenching diameter is 0.65 millimeter. Means very small, right? So what is the problem if it is small? Then fabrication of particular devices of flame flashback or as per the device is called. Okay, it is difficult, right? Even when you are going for high pressure of premixed hydrogen combustion, even this quenching diameter is even lower, right? If you see over here, this is 0.1, this is 0.2, this is 0.3. 0.3. How would you drill 0.3 millimeters? Even whatever it is micrometer of the drilling, the flame will go inside. That is going to be accident. So this is another challenge. And even laminar burning velocity. What is the laminar burning velocity means? If you have, this is the tube, let us assume this is the 4 meters tube, okay, and initially you fill this particular tube with certain fuel and air. You filled and both sides you closed, okay. Now you started ignition over here by sparking or something, okay. Now the flame will be moving towards over here, right? Now at what velocity the flame is moving, that is the flame velocity, laminar burning velocity, okay. Now here, whatever the fuels we are using, that can be starting from methane to any other carbon fuels of C12, H26, that way, right? All fuels laminar burning velocity is ranging from 30 centimeters to 50 centimeters per second. This is the range. Whatever all the combustors you are using now, that is in that range. Now, unfortunately, this particular hydrogen is 200 centimeters per second. Means how many times? 4 times or 5 seconds, right? Now you have habituated to running with certain speed. All of a sudden you need to run the 5 times that. Would you able to run? Not possible. Okay. Means here, if the laminar burning velocity is higher, that means the fuel is reacting faster, right? So this is the hydrogen is faster reactor. Then you can ask the question, what if it is reacting faster? That means if the hydrogen is entering inside the combustor, immediately it is burning. Then your flame zone is very small. When flame zone is very small, again please remember our slides of conventional and flameless combustion slide. When flame zone is very small with high energy, the flame temperature is higher. When flame temperature is higher, NOx formation is also higher, right? So, in case of hydrogen, there is no carbon, but problem is NOx formation. That is very high. Okay. So that is the burning velocity. Now let us talk about storage. We already have discussed storage, right? So we have 47 liters of cylinder and 200 bar pressure. Only 800 grams of hydrogen is there in that, right? The similar phenomena. See, this is 1 meter cube. 1 meter cube. Okay, energy content is this much when it is gasoline. Gasoline means petrol. Energy content is this much. And over here, if it is methane, this is this much. Whenever it is hydrogen, very low. That's what we expect. Okay. So this problem also we need to solve further. Okay. So now what we have got? This is the thing we have discussed. Now, where storage research is going on means how to develop high pressure cylinder. This is type 1, type 2, type 3, type 4. In case of type 4, you can store the gas up to 700 bar. 700 bar. Backbench boys. Okay, 700 bar. Fine. So that means whatever example we have taken, and here instead of 800 grams, we can store over here 2 kgs or 3 kgs. Okay, but still the solution is not very soluble solution like reaching to this case of gasoline storage or even this case of at least methane storage, right? Okay. Now that is the reason what we need to do. Instead of using hydrogen, we can use ammonia as the fuel. What is ammonia? That take hydrogen and take nitrogen, do some chemical process of hydrolysis process and produce ammonia. Okay, then you will be using this ammonia. Why should we use ammonia? See over here. Whenever ammonia at 10 bar pressure and ambient temperature, that is in the liquid state. Okay, as like your gas cylinder, storage is there, right? Your cylinder is there. Did you shake ever? When you shake, it is liquid, smashing inside. Now my question is, when it is liquid, how you are getting the gas to your stove? So what is happening over there? That LPG, okay, the boiling temperature is the ambient temperature when it is at 4 bar. So the cylinder is 4 bar. The cylinder surface is all the time exposing to the environment. It is evaporating continuously. That evaporating gas is passing over here to the stove. The similar phenomena here, the LPG is storing over here. That ammonia is storing over here. Okay, at 10 bar and ambient temperature. That is continuously evaporating and supplying to your needs. Okay, and here the advantage is ammonia is non-flammable at environment condition. It won't burn even if it is leaking. Only thing is health hazards are there. So luckily you can detect the ammonia leakage very well because it gives noxious smell. Immediately you can close it. The safe and you can transport it. And this ammonia at this particular 10 bar and atmospheric condition, the density is 690 kg per meter. Just like your gasoline, right? That is. Okay. So now let's go back over here because we missed it. Okay, this particular thing. Okay. Storage wise, the problem is solved. The hydrogen storage and ammonia storage, the solution came over here. Okay. Now what is the problem with ammonia? The ammonia problem is like our conventional fuels laminar burning velocity, as we mentioned, 30 to 50 centimeters per second, right? So hydrogen, what you call 200 centimeters per second, which is very fast moving. Contrary, this particular ammonia is 6 to 7. Okay, you can call this particular as snail and this particular as your motorbike, and that hydrogen you can call it as bullet train. Okay, you are habituated to run with the motorbike at least. Now you need to walk with snail. How long time you can walk? For a few minutes you can walk, then you will be frustrated. The similar phenomena in case of reaction also. Since laminar burning velocity is very low, that means what? Reaction also low. It is not reacting, right? Okay. So, but this is the fear. This is the fear. Okay, need to do something, right? And another problem is over here. NO formation. That is the fuel based NO, means fuel NOx. The fuel NOx is dominating over here. That we are going to see over here now. Okay. So initially, who has identified this ammonia as a fuel means this is not new. During World War II, that time itself, when diesel scarcity was there, then ammonia has been used. But the problem is because of incomplete combustion, the ammonia emissions are coming. That is creating huge uncomfort over there. Okay. Then meanwhile, the diesel issues might have been solved. Then they have stopped using this ammonia direct injection in internal combustion engine. That means they have identified it as the fuel. Now recently in Japan, so this ammonia has been used as a fuel. Okay, reaction was taking place very well. Okay, but these are the issues. When you are heating the combustion, temperature is around over here 500 to 600 centimeters per second, right? Sorry, degrees means Celsius. The complete combustion was happening over here. Means ammonia leak was not there. When the preheating is reducing like 450 Celsius, then amount of LP means ammonia was leaking to the environment, right? So this is one problem. When complete combustion was happening, the NOx formation was a lot over here. See, NOx is like 1000 ppm. Even we were worrying in case of conventional fuels, 20 ppm, 30 ppm, we were worrying. Now, ammonia is using as the fuel very well, right? But huge amount of NOx is producing, right? Combustion research upon this ammonia has been started from that point. Okay. Now, certain research have been taken place by Mahendra Reddy et al. Like over here, when you are burning pure ammonia, suppose this is the case, the pure ammonia, right? Then this much of NOx, see over here, around 600, 700 ppm of NOx was absorbed. When it is simply pure methane, right? This is just 20 ppm, right? So now, as you know, the ammonia is slow fuel or lazy fuel, you can call it as, because its burning velocity is 6 to 7 simply. Certain things need to be added. Okay, you cannot walk with the sail, but you love snail. So what you are doing, you are taking the snail on your vehicle and going. Similar phenomena here, you are adding certain amount of hydrocarbon fuels over here. When you are adding certain amount of hydrocarbon fuels, right, what is happening over here? What we usually expect, the emissions, NOx emissions should be like this, like interpolation or anything. But when you are adding certain amount of hydrocarbon fuel, NOx is increasing over here. Okay, NOx is increasing over here. That is the time of ammonia and adding certain hydrocarbon fuels. The same time, we also experimented. This is the combustor we have developed in our laboratory. This is like a recuperative combustor. Why are we calling recuperative combustor? Means if you see, air is entering over here, and this is the annular zone. This blue is there, right? This is the annular zone. Upon this annular zone, air is flowing over here. Okay, and fuel is entering from this side, right? And then the reaction is taking place in internal chamber over here. Okay, then these walls of this internal chamber is hot, means high temperature enough. So that is the reason the fresh air, whatever it is coming here, that is preheating. That technique is called recuperative, right? So in this particular thing, okay, so we have utilized methane and ammonia over here. Okay, we have combusted. Okay. So this is pure methane flame. This is ammonia and methane flame over here. as we have discussed earlier, right? So our emissions also in the range of 1500. The reason is like this. We have seen in case of Maradizonal study, right? So when we are mixing certain hydrocarbon fuel over here, then yeah, this is. When we are mixing hydrocarbon fuel, the NOx is increasing, right? So similarly, in our experimentation also we have observed this. So this particular paper got accepted in a chemical engineering journal, which is high impact of 15 around, okay, within very short duration of review, right? So then after, to stabilize the flame over here, okay, means flame is stabilizing outside the reactor, we have inserted inside the porous bottle, right? So then flame is stabilizing completely inside the combustor. Even it was possible us to go even higher thermal input, like this. Okay, this is the porous body over there. The flame got stabilized inside. Very well, right? Okay, but however, we are able to burn the fuel successfully, but NOx emissions are predominant. Then how to reduce the NOx emissions? So meanwhile, in the next generation of research, within this 1 decade only, whatever we are talking, this 1 decade, and then rich lean technique. What is the rich lean technique? At the bottom of the combustor, we are burning the rich ammonia, and then at certain location over here in the downstream of the combustor, we are injecting certain oxidizer over here. Whatever NOx is formed over here, that NOx is reburning over here, right? So let us see over here. This is the NOx production in the rich area. This is completely NOx production in every reaction. These are the major reactions over there, right? This is the NOx production. Whatever so produced NOx in the excess air, whatever we are giving in the lean area, okay, so that NOx is burning again and forming nitrogen over here. That's what we call it as rich lean technique of NOx reburning, right? So based upon that, okay, with experience of our tubular combustor and rich lean technique, and then we have developed this particular combustor. This is there in our laboratory. Next slide, I am going to show you the setup. So what is that? This is the 4 well-stirred reactors are in series. This is combustor line. 4 well-stirred reactors are in series. So whatever this is the tangential air injection scheme is there, that is producing swirl inside. That is the vortex formation is happening. That's what recirculation is happening inside the combustor. The flame is stabilizing very well, right? That means what? The flameless combustion concept we have studied. Well-stirred reactor nature we need. So this is producing well-stirred reactor. Okay. Here we have taken 4 well-stirred reactors in the series. And what more we need to apply? Rich lean technique. So that's what the total fuel we are giving over here. In the first 1 reactor or 2 reactors are rich condition. In the second, means this 3rd reactor and 4th reactor, the pure oxidizer is entering, that is the lean. So rich lean technique also adapted over here. So this is our combustor, what we have fabricated. This is the beginner, like this is the 4 meters height, 4 feet height, is 1.2 meter, and even diameter of 40 centimeters. 40 centimeters diameter, 120 centimeters height. So here we have given provision that if you want to run 2 stages also you can run, 3 stages also you can run, 4 stages also you can run. But it is not possible for single stage actually, right? That way we have developed this combustor. The inside chamber, we have 4 of these chambers inside. So initially we have stabilized the flame with LPG. At the bottom if you see, this is this particular. Okay, this is the pilot flame, pilot burner. Okay, everything is our lab made only, no commercially purchased. Okay, so we have stabilized the flame inside for certain time of total walls are getting fitted. Then after ammonia is started injecting, then simultaneously LPG is reduced. At one point, the combustor was completely running with ammonia. Okay. So this is the experimental setup, and it is giving you what all equipments we have used, what all instruments we have used in our laboratory. So this is the combustion is happening inside. You can very clearly see. and these are the flames inside. This is for case of 4 cases combustion. And here one interesting phenomena has been taken place. This is like C10. 10 means what? Kilowatts. 20 kilowatts, 30 kilowatts, and 40 kilowatts. S means secondary fuel is added. In case of 20 kilowatts and 10 kilowatts, these two, okay, high amount of NOx has been identified. Okay, so why this particular phenomena is happened? When you have 4 stages, when you are running combustor at 10 kilowatt, the sufficient amount of, suppose if you take equivalence ratio over here, right? In this case, X quantity of oxidizer you are giving. In this case, almost 3x quantity of oxidizer you are giving. But this X quantity of oxidizer to be passed in all 4 combustors. So whatever air is entering in each combustor, that inlet velocity is reduced over here for these 2 cases. When inlet velocity is reduced, the proper stirredness has been not achieved over here. Means well stirred reactor nature, whatever we are looking for, that has not been stabilized over here. Right? So that is the reason over there. Conventional kind of wick kind of flame has been stabilized over here. That's what the emissions are very high over here. For case of 30 and 40, the flame was stabilized very well over here. Okay. With this understanding, for case of lower thermal inputs, okay, so then 2 stage may be suitable. That study also we have done, that we are not showing over here, it will be lengthy. Okay. These are different flames. This is upon 2 stage you can see over here. Okay. So even in the 2 stage also 10, 20, 40, 60 kilowatts we have tested over here. Okay, very well distributed, even mild combustion kind of phenomena. Okay, so very well swelling flames with pure ammonia gas, stabilized over. Okay, this work has been conducted by Srinivas Rao. Now he is in Dubai working for certain gas turbine company. Now left what we have done. So thing is that here in case of ammonia, you have seen 2 cases. The first case with ammonia and hydrocarbon fuel mixing. The second case is with the pure ammonia mixing. In both cases, if you see, first case obviously 1500, 1600 ppm of NOx we have seen. In case of second case, right, so your NOx ppms were even certain high enough over here, right? Certain high enough over here. This is not in case of, this is NOx per kilowatt over here, right? So still certain amount of is there. Then what to do for that? And also here the combustor is very big. The combustor is big enough, right? So then what to do? But this is applicable for land-based applications, that can be land-based gas turbine or industrial furnaces. But in case of gas turbine engines, the combustor should be compact enough, right? Then this particular technique we have used. Again using the mild combustion phenomena. This is the certain burner, pre-mixed burner. Upon this pre-mixed burner, initially we are passing LPG. Okay, this LPG is burning in this particular area. Pre-mixed means fuel plus oxidizer both fed to this, right? That is burning over here. After that, we are injecting ammonia radially. This is the ammonia supply to this, and that is distributing radially over here, right? So then this ammonia we are injecting in hot gases. What gases are those? Those are simply high temperature inert gases, because combustion already has been taken place over here, right? So these hot gases are steam and CO2 probably, right? So this is our experimental setup and instruments we have used over here. So here you can understand the phenomena very well over here. This is your bottom burner and flame has been stabilized here. Upon this, we have injected this ammonia radially. Okay. Even we have conducted for every case. In case of combustion, actually, instead of running the combustor in the laboratory for many cases, that is expensive. Means fuel you have to run, compressor you have to run, and every time you have to measure. So to avoid those all, you have to run the CFD simulations, right? As you know, the combustion simulations are complicated than other simulations because the reaction mechanisms also you have to calculate. For other cases, usually the fluid dynamics, heat transfer phenomena only. Here, along with your fluid dynamics and heat transfer phenomena, the chemistry also you have to calculate. The chemistry is not simply 2-step, 3-step reaction. right? The species are like 50 species, 60 species, these many species we have to calculate. So that's what initially we do simulations. Based upon the simulations, we design the combustor. Based upon that, we fabricate and we test it. Then whatever the testing results are there, those are close to the simulation almost. Okay. So these are our simulations over there here. And in this particular experiment, we have observed one tremendous phenomena over there. Even we could not believe ourselves. What happened when we were measuring the NOx emissions? The instrument was showing 2 ppm. 2 ppm. And then we got doubt upon ourselves, or otherwise the equipment, means measuring instrument. And then we moved to the other cases like these cases, right? Other cases, and then we tested our equipment. For those cases, whatever 200 ppm, 300 ppm it's supposed to show, it was showing. And again we came back to this particular case, okay, and we tested, again it was showing 2 ppm. Okay. So that is the case of when you are injecting ammonia in case of hot inert gases, okay, that is completely reactive. However, when we are moving towards higher thermal inputs, higher thermal input means the mass flow rate of fuel is increasing, the unburnt fuel was detecting at the exit. So to avoid that, we placed this particular porous bodies over here. As you know, the porous body is holding huge amount of the heat, as well as it is creating the flow disturbance over there, right? So very well stabilized flames are absorbed over here. For these cases, if you see, the NOx emissions are 2 ppm, 3 ppm. Right? So this particular work has been carried by the gentleman is sitting over here, Uday. Okay, so even earlier research of Srinivas has been published in many top journals, as well as this particular work also has been published in many top journals. And we have applied so far 5 patents upon this particular 2 works. The patents are in process now. So this is the answer. So what we have seen in previous combustors, so certain significant research need to be conducted. Then you have to design the combustor. Then you have to be tested it, and then you have to certify it like patent kind of thing. Then only the product can be delivered to the people, means end users, right? So now instead of that, the immediate solution means mix certain amount of hydrogen along with the conventional fuels, right? So this is the combustor what we have prepared over here. If you see in this particular combustor, this burner, I am not sure whether you are able to see very clearly. Okay, in this burner, the central one is liquid fuel injector, right? Surrounding that, this is the swirler with high swirl number, right? Surrounding that, this thing, many number of holes are there over here. Those are holes for providing the hydrogen, right? And this was very expensive for us because we have already discussed our quenching diameter should be 0.6 millimeters. Okay, so micro machining has been done over here. These all holes of 54 holes, I think so. 54 holes has been drilled of 0.6 millimeter. And you can ask over here, but this is not the pre-mixed. This is the non-pre-mixed. That means only hydrogen is coming out. Then why should you take 0.6 millimeter? You can go 2 millimeter, 3 millimeter. Okay. You by mistake, any reverse flow phenomena, the nearby you have air over here. If you take 2 millimeters, air enters inside, then flame will be flashing back. Okay. To avoid that risk also, we have considered as same as like pre-mixed case, and we have provided the 0.6 millimeter holes over here, right? That way you can see over here, by energy ratio, 30% of hydrogen is added over here, okay? So here what happened, when we are adding the hydrogen from 5%, 10%, 15%, 20 up to 30, the flame brightness has been increased, like yellow flame to whitish flame kind of, okay? And also combustion was very clean, means when we are running this pure kerosene upon this particular combustor, you might have seen over here, this is the quartz glass, okay? So within few minutes, the quartz glass is becoming black. What is that black content? Soot, okay? When you are adding certain amount of hydrogen, the soot content was almost nil, and this tube is as like unusable. That means addition of hydrogen is helping you to complete consume the carbon content, which is soot formation. Also, it is suppressive, right? So this is the phenomena. And one more thing what we have done over here, we have added a steam over here. Okay. Why we are adding steam means what combustion phenomena is suggesting us, when you add steam, that is producing OH radical, hydroxyl radical. How many of you understand, I don't know, but this particular phenomena, I don't have any picture also to explain you very well. Okay, when you are in high temperature zone, when you are injecting the steam, okay, that is producing more OH radical. Whenever OH radicals are more, then reaction rate is more over there, right? So in that way, to achieve that phenomena, we have injected steam also. Then this particular conventional combustion, when we are adding the steam, has been transformed into the mild combustion phenomena. See, compare these two things. In this steam is there, steam dilution, here no steam is there. Okay, and even here hydrogen is there, here no hydrogen. Okay, the quantity of thermal input is same. You can compare these two images. Okay, this is very bright flame, yellowish flame is there. This is almost transparent flame is there. Both are same purpose, right? Okay, so this is the impact of hydrogen when you are adding to the hydrocarbon fuels. Okay, this work again has been performed by Mahendra, who is sitting over here, right? So these all are under the publication process now, right? Yeah. Okay, so what slowly we are moving? We started with hydrocarbon fuels. There, what are the challenges? Then, what is the novel technique? From that novel technique, but still, we need to move towards the non-carbon fuels. So we move to the hydrogen. Hydrogen again giving you lot of challenges like flame stabilization wise as well as the storage wise. So that is the reason we converted the hydrogen into ammonia, right? Then ammonia we have got, right? In case of ammonia also, certain high amount of NOx has been absorbed. To suppress that, few more techniques we have identified. Then ammonia combustion was over. Now, the infrastructure is adding more. What infrastructure? The producing hydrogen itself is involved with a lot of infrastructure. Because hydrogen is not like natural resource like your crude oil. From the crude oil you are getting natural gas or otherwise LPG, kerosene, diesel, petrol, and even light fuel oil, heavy fuel oil, bitumen and petrol. These are all different products of that, right? But this hydrogen is not like naturally available. We are producing ourselves, like electrolysis process, right? Or otherwise gasification and methane reforming and forming syngas. Okay, these phenomena, these are the things man-made kind of hormone. That itself is involved with a lot of infrastructure. And again, what again infrastructure is adding? Convert that hydrogen into ammonia. But transportation is in case of ammonia, that I agree, right? And again, this ammonia, certain challenges are there. Okay, so that's what another channel, other group of the people have simultaneously working upon hydrogen combustion also, right? In the same direction, we also moved over here. This is pure hydrogen combustion, right? This is a pure hydrogen combustion. Anyhow, to achieve low NOx, only technique is well-stirred reactor, nothing more. We have to make it as a well-stirred reactor. The local reaction should be distributive reaction. Because of that, the temperature is reducing. That is very well fitted over here in case of hydrogen combustion, because hydrogen is high in reaction. In a small zone, the hydrogen is burning and giving a lot of temperature. Okay, because of the NOx is forming a lot. Even in case of pure hydrogen and air at stoichiometry, the NOx emissions are again thousands. Okay, NOx emissions are again thousands. Then how to solve that also? Then in that case, only solution over here, distributing the flame very well and even going towards the lean whatever it is possible. When you are going lean side, what is the advantage to you? Lot of air you are putting in that. Obviously, heat energy release is equal to mCp delta T. When your mass is increasing, then temperature should be reduced, right? Then NOx will be reduced, right? So that way. And what is the other problem over here? When you are putting huge amount of the oxidizer inside the combustor, the residence time is reducing, right? Means in this combustor earlier 1 kg of air is going, the residence time let us consider 10 seconds. Now, instead of 1 kg, I added 5 kgs. Then obviously residence time is 5 times it is reducing. Within that small time, it has to be reacted well. Okay. If it is not reacting, again unburned fuel is coming out. Right? So that's what we have done over here. We have taken it as well-stirred reactor and a recuperative reactor. I hope only few slides are remaining. Right? So we are passing air over here. This air is actually, this is the annular chamber over here. This air is passing upon walls of the combustor, right? And then this is with many holes are there over here. Through these holes, air is entering this at a high velocity. The same time, the oxidizer is also, fuel is also entering at certain high velocity over here. That means these 4 jets of, or certain 5 jets of air is there, in between hydrogen is there over here. Okay. Now, this exit is other side over here, not even this side. So whatever we are injecting, those all fuel plus oxidizer at certain high velocity need to achieve, means reach over here. Then again it has to take turn and go back over here. Right? It is passing over here and going back over here like that. That way, this is like a well-stirred reactor nature it is happening over there. Right? So we tested over here, and even we have gone to 0.2 equivalence ratio up to, and here we have given this particular quad window over here to observe very well, and then these flames of very well distributed flames have been observed over here. And same time you can see over here, right? Suppose see, throughout this quad you are able to see well distributed flame. In case here what is happening? You are not seeing this kind of distributed flame. That means the equivalence ratio is less over here, means rich over here. That is the reason compared to over here, air quantity is 2 times less. So velocity is less over here. That is the reason the jets are not reaching up to here. The jets are reaching up to here and getting reacted and escaping. Okay? That is the reason flame fronts are appearing over here, like this. Fine. So, and another, this particular combustor here, my student, Vibash was working upon this particular, he is a second year student over here. And this is another very important concept over here. Okay, here what we want to do, we want to again go to the lean combustion, 0.2 equivalence ratio, to suppress the NOx again, right? To suppress the NOx to 0.2 equivalence ratio level, to stabilize the flame, we have to preheat it, right? So we have given here 3 layers of preheating over here, right? The air is entering here, it is passing one fold over here, and again taking another fold over here. Upon this combustor of the wall, many fins also have been provided over here, because fins are enhancing the heat transfer, okay, and surface area also it is interacting very well. And then in these 2 layers, then air is entering over here, right? By reaching over here, air is sufficiently preheated. That is one thing. The second thing is actually, in this particular case, walls of the combustor was around 400, 500 centigrade. Okay. Anyhow, we have insulated like this. Okay. Whenever it was testing on the bare surface, and here it was hardly 100 or whatever. Why? Because the cold air is entering here, then after passing over here, right? So direct interaction is not done. That means even though this combustor also we have insulated very well, the heat losses by the mode of convective as well as the radiative is very less over here. That means your thermal efficiency by this particular twofold of recuperative nature is increased very well, right? So next, coming to the fuel injection mode, here these are the 8 fuel rods over here, fuel tubes, we should not call rods, fuel tubes, and each fuel tube we have 8 holes over here, right? So in this case, in this first case actually, first entering and leaving, so that is giving you well-stirred nature. Here, without achieving the well-stirred nature, self-distribution is required, because high velocity hydrogen is injecting over here, that's what jet is achieving up to here. Meanwhile, hot gas also coming. That means in this entire combustor, the flame volume is like this. Okay, flame volume is like this, distributed flame. Means fuel is even distributively injecting inside the combustor, right? And even we have given one provision over here, these fuel nozzles, you can turn it to any angle. That means, suppose if you take this is the fuel tube, now holes are like this. If you turn this, then it can be 45 degrees angle. And if you turn this, even it can be 0 degree angle like horizontal. That in fact also we can study over here. In case of 90 degrees vertically up, the hot air is also coming, the fuel also injecting vertically up. In that case, in the exhaust, certain amount of hydrogen has been detected, around the 300 ppm like that, right? So now, when we incline it to 45 degrees, okay, the hydrogen is injecting in the angular location like this. Meanwhile, the oxidizer is coming in this vertical direction, both are interacting and complete combustion is happening, right? In the exit, the fuel quantity was almost very minimal. Okay. Then we tried with horizontal location, right? That was the problem was when we are injecting horizontal and air is coming over here, instead of distributive nature, there only flame disk kind of phenomena has been happening. Because hydrogen is coming like this and air is coming here and both are mixing there only. And also, since the flame is stabilized around, these fuel rods also reach to the red hot. That fuel rods or fuel tubes are like flame initiators or other flame igniters kind of thing happened. The flame zone was very small over there. Because of that, NOx emissions have been increased. Okay. So, however, these are the flame phenomena observed inside of the combustor. Okay. So, at the exit, very low amount of NOx has been identified. These two things results we are not producing because recently this particular thing is worked by Achita, Ajit Kumar Behra, I'm not sure whether he is here, yeah, he is here. Okay, so now these two things we have applied for the patent and as well as the planning to apply for the paper, so results are not disclosed over here. So please let me conclude now. So yes, like in this present session, so we have started about what is the problem with pollutant emissions to the human being, as well as in case of conventional combustion, how to suppress them. Like many techniques, like started with attack combustion and reached towards the flameless combustion. The emissions have been suppressed very well, but still the CO2 cannot be suppressed. Okay, so that has to come out. But if you want to suppress the CO2, then you have to change it to the non-carbon fuel, that is like hydrogen. Hydrogen again, many challenges are there. Then converted into the ammonia. In the two streams of ammonia combustion as well as hydrogen combustion, we have this given total combustion community is projecting in the two directions. So in our laboratory also we are projecting in the same. So here two channels are there. Suppose this is the method of hydrogen production, right? If then hydrogen can directly be utilized over here, or the hydrogen and nitrogen are forming NH3 and transportation is very easy, right? Then again, directly consuming the ammonia or otherwise cracking the ammonia. Other phenomena is there over here. You can crack the ammonia back. That is again adding additional infrastructure. That means when you pass the ammonia in high temperature tubes, okay, that is like thermal cracking we can call. That ammonia will be splitting back again to the hydrogen and nitrogen. But is the thermal cracking we can call it simply. If the tubes are coated with certain materials like nickel or certain materials like platinum and ruthenium, right? Then temperature of preheating will be reducing. In case of pure thermal cracking, you need to take to 1500 Kelvin. Okay. In case of nickel, next step is nickel. At 800 Kelvin, 900 Kelvin in between, the cracking will be initiated. When you use the ruthenium, and again it will be reducing. When you use the platinum, the coating, again it will be reducing. That is the cracking phenomena. In this particular direction, Gangadhar is working. Okay. That is unfortunately we don't have the equipment for that. So that is the reason we are working numerically. Okay. And this is the conclusions. These are the references. Okay. So why in every slide this Barnabite energy systems is there means. So based upon these combustion systems, so we have started our startup over here. Okay. So that is the Barnabite system. So this is like related with the combustion equipment as well as gasification, one more sub area, and as well as some CFD solutions, as well as the combustion. Whatever combustion we have produced, we are ready to sell to anyone because we have published as well as we got a few patents also. So that is the phenomenon. Thanks a lot. Thank you. Thank you.
Yeah, Dr. Reddy, thank you very much for your enlightening talk on challenges in non-carbon, ammonia, hydrogen, fuels combustion in industrial and gas turbine application. That's what it started with the pollution regulation. Then it was about the classification for hydrogen. That's what is also very informative for us. Hydrogen challenges specifically for the flameless combustion, storage, flame speed, its property. Those all things need to be considered when we are talking about the application of hydrogen for the combustion for different applications. Then we were having the attraction towards the ammonia. That's what is initiation, very good initiation from IIT Kharagpur, that too from mechanical engineering department. What all ongoing research we are having for hydrogen combustion, for ammonia combustion in combustion lab at IIT Kharagpur, that also is covered in this talk. And mainly with the challenges in terms of ammonia, that's what people they are talking about, the future application for maybe combustors, especially for the burners or maybe for the land-based power plant, and even people they are talking in terms of application for the aero engines. So let's see how we will be moving forward with this. We are closing our session. I would like to yeah. So we have a few questions from the audience. Yes.
I have two things out. Ammonia and hydrogen, their densities are so different. So while mixing it is possible because hydrogen already has not much ammonia in their density. So how do you tackle that?
So in case of combustion or
While mixing it, because you're mixing it, then it's coming to
mixing when we are maintaining certain velocity, suppose absolutely. What we have shown over here, a very nice question, need to discuss few minutes. So we have demonstrated over here either ammonia combustion or hydrogen combustion. The certain combustion things also happening, the 40% hydrogen and 60% ammonia. Okay, so these combustion systems also many are there, research is going, but we have not done that area. So here, when you are two phenomena are there, in the same tube you can pass, or multiple jets also you can use in the same combustor. When you want to mix up on the same tube, you have to maintain certain momentum, means velocity you have to provide. Then it will be going together. It will not be within that tube itself. It will not be separated. It will be mixing together and going. Or we will be using 4 jets of methane and 4 jets of ammonia and 4 jets of hydrogen in the combustor. That way also we can.
hydrogen combustion is not very dangerous.
No danger. As like other fuel, only thing certain issues are leakage issue.
How do we decide that hydrogen link from fuel
Combustion. Yeah, that is challenge for every combustion system, including even hydrocarbon fuels also. So everywhere actually mixing is the main phenomena. Fuel oxidation mixing, and before leaving the combustor, all fuel should be reacted inside the combustor. So through that way, we will be conducting the computational fluid dynamic analysis. From that result, we will be finding out our combustor shape. Even we are using some solars, or in some cases, the combustor is like a diverging kind of shape, and then cylindrical kind of shape. And certain cases, the geometry itself is like a reverse flow phenomena. These all are like to enhance the mixing as well as stabilize the flame within the combustor very well. So CFD is required. Simply, we cannot gauge the length and diameter. So at this point, I would like to mention one particular important thing. In India, ammonia combustion is started in IIT Kharagpur only, in our lab only, in 2019. The first paper in India based upon ammonia combustion is Mechanical Engineering Department, IIT Kharagpur. And maximum number of papers on ammonia combustion and hydrogen related thing are there from IIT Kharagpur Mechanical Engineering Department. Thank you. So
I have one last one question on carbon capture. So in India, how this
done, or whether we are into carbon capture or.
Yeah, research is going on, carbon capture, even huge funding is also coming
No, it is
up.
not a research in terms of real world
The real world application, suppose that is required, majorly required for countries like India. The why? Because in other countries actually we are using certain other fuels and we are using coal majorly. Whatever thermal power plants are there, those are necessarily captured and even not very difficult because we are living by the draft only. So through that we have to capture it and then cooling down and separating the water and all, and then like that we can, it is possible very well. But still we have to, instead of cryogenic methods, we have to go towards catalytic methods. That will be more accelerating and even more compact also. But catalytics, conventional method of capturing it and compressing it to the high temperature, high pressure and cooling down it, then CO2 is converting into the liquid. Gaseous CO2 is converting into the liquid and can be stored easily. That is cryogenic as well as other method, conventional methods. The catalyst to be produced very well. That research is going on now. That will be implemented very well, I believe so, in the future.
Thank you. Any other questions?
Any questions?
Any question from audience? Thank you. Thank you very much.
Thank you once again.
Now I request Professor Manjunath to offer memento from Institute of Engineers, IIT Kgp chapter.